All right, thank you. Thank you very much. Thank you for the introduction. Yeah, and as Michael said, this talk is going to be much more low-tech than Ron's talk. I know he's pulls out a lot of analytic firepower. We're going to be going through really discussing at a sort of bit of a liberal arts level here, but I think important topics to understand what different types of statistics do, what types of problems they can be applied to, and try and think a little bit about kind of why they work. So this is very much aimed at the practitioner. And in a way, my hope coming out of this would be, if you're sitting in your office and you get pitched by some consultant with some new shiny object, you've got some metrics and measures you can use to decide whether you should take the meeting, whether it's plausible that this method that they're proposing is going to work. So there's a million buzzwords out there around big data, data science, AI, predictive analytics. We hear them over and over. And as I said, I'm trying to really, by the end of this, I want you to sort of understand what distinguishes one of these from the other. And there's a great example that we can use that probably everybody has. I can't see the audience. The problem with this new format, I can't tell, average age and what have you. But I would imagine everybody out there, you all live somewhere. Probably most of you live in a house, and you face the problem of buying or selling a house. And so, how do you go about that? You pick your neighborhood, and then you walk around and you look at some houses, and then finally you settle upon one, and you think, yeah, this is where I want to live. I want to make an offer on that house. And so you've got a problem of statistics is, how much am I going to offer? And today that process is made enormously easier for us than it was maybe 10, 15 years ago, because you whip out your smartphone, you go to Zillow, and you type in the address, and it'll tell you, you see here to the dollar, exactly how much it thinks this house is worth. And how has it done that? Well, they've obviously got a database of all the transactions that have happened countrywide. And you see off to the right here, they have pulled out some comparable locations. And you can see that they're regarding comparable, once you've fixed the geography, number of bedrooms, number of bathrooms, and square feet kind of defines comparable for them. And we've got a list here of 5 houses that have recently sold that are similar to this house. So at this point, we've got some statistics. We can start to do some learning from data. And the most basic type of statistics we would do would be some descriptive statistics. So we would take those 5 numbers, and today, we wouldn't think twice about averaging. We would take the average and we would maybe look at the range. It's an interesting fact that historically, it took mankind a very long time to get comfortable taking the average of multiple estimates. I think it was into the 1700s before that became a common practice. Before then, people tended to look at a set of data points and try and discern which was the best one, particularly in astronomy. There was a lot of competition between countries. And, the French astronomers didn't trust the English astronomers or the Polish astronomers. And so there was a lot of reading the details of the numbers that went on. So just simply taking the average is actually a big move forward for mankind. But we take that for granted now. And then, we might do some more exploratory data, which is really making claims about the current sample of data that we've got. So it characterizes sort of exploratory data analysis and exploratory statistics. But obviously in this situation, that's not good enough for us. It's very unlikely that the particular house that we've selected has been recently transacted. And so we need to generalize from these comparables because our house is going to be similar to, but not identical to other houses that have sold. So we are facing a problem of predictive modeling. We are trying to estimate the value for an out-of-sample unit or observation. And I point out here, this is exactly the insurance problem that you face with every single policy that you write, because even if it's a renewal policy, the insured in the coming year is not the same as the insured in the prior year. An auto policy, the person's a year older, years more experience, they might have had change of car, change of personal situation or whatever. They are essentially a new unit that you're trying to predict a loss cost for in the coming period. So this is the bias perspective of the home transaction. Those of you who've also sold houses would understand there's a different perspective, the seller's perspective, which is somewhat more complicated because the seller has gotten a broker probably telling them, you know, this house is kind of old and fusty, and you probably should think about remodeling the kitchen or painting it or landscaping or adding about that. All of these things that are going to make life easier for the broker to sell your house. And you need to understand, well, if I do each of these things, then there's going to be an investment that would be fairly easy for me to quantify and get a quote. But what's it going to do to the value of the home? And so you want to understand really, you want to do some inferential statistics on the prices of the units that are for sale so that you can discern, all right, add a bathroom adds X tens of thousands of dollars to the price, or remodeling the kitchen or what have you, is a problem of understanding the drivers of the prices that you're observing. And that's the process of inferential statistics. So we've got a number of techniques for doing these things, and a lot of them boil down to a process that we call machine learning, which is generically some algorithm which allows a computer to learn, build, and improve a model from more data. And a lot of the things that we take for granted that we use day in and day out, certainly a lot of my examples are going to be drawn from actuarial practice because that's kind of where I come from. You know, generalized linear models used all the time in rate making, logistic regression for frequency analysis, decision trees, and so forth. The CAS, Casualty Actuarial Society, has an institute which is actually credentializing people in this area, and they have a CSPA credential, a certified specialist in predictive analytics, and it's focused on these types of techniques. Now, we take for granted that we know these methods work well. You might be scratching your head and thinking, well, how else could you do it, right? You know, what other approaches would there be? Well, two examples of things that are not machine learning that sort of, if you go back historically, were maybe more popular, is an idea of an expert system or a knowledge base. And the thought process here would be you gather some experts together and they would opine on what the important factors were, and they would sort of, you know, put out some sort of schema for how they thought things should work. But that's obviously a fixed thing. That could get the answer wrong forever, and it would never change itself. And you can't just press a button to update that. So that's an example of a non-machine learning type. These models, as we know, they tackle a broad range of problems, often spectacularly well, but you know, almost always providing some sort of form of assistance. Classification, regression models, you know, machine translation has come along enormously. Spell check, anomaly detection would be things like fraud or spam detection and so forth. Right? So a wide range of applications of these techniques. Now, if you're paying attention, I sort of started this off by saying, how do you know the value of the estimate of a new home? Well, you go and you look at some comparables. Now, you should have called me potentially on that, because the fact that we have somehow abstracted out of all the information about a house, that its location, its square feet, number of bedrooms, number of bathrooms are kind of the 3 or 4 key variables, encapsulates an enormous amount of domain expertise. And we might wonder about, well, could we go back to the raw data? Could we look at some more fundamental data and kind of throw that into some sort of machine learning algorithm and get a better answer out? And it's, you know, raw data is an interesting concept. So there's a little quote here about raw data is both an oxymoron and a bad idea. And to the contrary, data should be cooked with care. If you sort of think about it, it's hard to envisage what actually is raw data, right? I mean, it's like, it's the hash, that is the raw data. Anything that you take from there is a measurement and is no longer raw and is subject to the, you know, this measurement error, the bias of what you chose to measure, and so forth. So this idea of collapsing kind of low-level data down into a very few quantity of numbers that really tell you what you need to know about the risk is a big simplification and a powerful part of the modeling process. It's the data representation. And we can kind of illustrate this with, I'm going to give you a little test here. Normally, I'd have everyone in front of me and we could do this with a show of hands. And I don't want to stress everyone out, but no one has ever got the answer to this question wrong. So you should pay attention here. We're going to be on the honor system. I'm going to show you 3 homes. This is home number A, this is home number B, and this is home number C. And these 3 homes are all within about a mile of one another. They're in the suburb of Chicago. And the question is, I want you to look at these 3 pictures and I want you to, in your mind, rank these homes from the one that you think has the lowest market value, the middle market value, and the highest market value. And I don't want to cause flashbacks of stress to exams to the actuaries on the phone, but this is a triple true false kind of situation. Just look over these answers here and select in your mind what you think the answer is. And I'll just give you a moment to do that. So hopefully we all selected that number 2 there is correct, and that B, the white upper right house, was the cheapest house. Number A, pretty nice house, was a sort of intermediate house, and then number C on the lower left there was the most expensive. And for your reference, there's basically an order of magnitude difference between these houses. They're about $300,000, $900,000, and $2.7 million was the sort of. And you could do that, I would guess, if I prepped you for this, maybe if I gave you like 15 or 20 seconds, you could have told me the answer to that with a very high degree of confidence. Now, this is the MLS listings for these houses. So this is a sort of fairly much structured text description. It's got, the rooms and information about the size of the lot and the house and what have you. And if I asked you to scan through this and tell me rank the same 3 houses, I suspect that would take you quite a lot longer, right? It would take you a few minutes just to even read this, and then you'd need to sort of like circle out, okay, to get to this, you'd know in your head what you would be looking for. I guess essentially, it's got the price there, but it would take you quite a while to figure out the answer from this. And what this highlights is that there are things that our human brain is just wired to do that we do extremely well, kind of without thinking about it. One of those is processing images. We can do that very quickly. And you look at the photograph of that house, you could tell stories about who would be likely to live there, right? Where's the doctor going to live? And where's the custodian going to live? And, who's most likely to have a domestic helper, and who's going to have, 3 cars or whatever. You can just tell that at a glance. We're kind of hardwired to do that. On the other side, computers are really, really good at processing structured text, and they could do that very quickly. So they would be able to read in the text I had on the previous slide, summarize that up, and probably come to a conclusion from that. That would be very easy. And we can sort of put this to the test for those of you who've done some programming. If I said I want you to create a computer program which is going to, the task will be, I'll give you 3 homes and you rank them. Which system would you try and program? One that started with 3 pictures, or one that started with the text? I'm guessing you'd all say, hey, I'll start with the text. And I'd imagine if you had access to Zillow's database, that's less than a day's work, right? You could crank out a system that would be very accurate and would rank 3, geographically approximate homes very easily. If you had to start with the photographs, you had to run a team, and it would just take much longer to be able to do that. So humans excel at a number of problems that computers find very, very hard. And this gets us to this idea of artificial intelligence. So artificial intelligence is a problem domain for solving problems that people find easy, but computers find hard. Okay, so we talked about image recognition, holding a conversation, voice to text, reading emotion, catching frisbees, right? It'll be a long time before we can build a robot that would catch a frisbee as effectively as a dog. And these skills, bringing out dogs, there's a lot of biological brains sort of appear to be wired in the same way, and they're all good at solving broadly the same things. So AI, problem domain, solving these types of problems that people find easy, but computers find difficult. And the basic premise here is that people kind of have gotten a long way with a single trick, right? Because as we've learned more and more about how the brain works, it appears to essentially use a single algorithm to solve every task that it faces. Okay, and this was actually an insight that was only reasonably recently sort of gleaned. Previously, machine learning research was very fragmented and took a different approach for, say, language processing or visual, speech recognition and so forth. But today we recognize that the human brain and then AI leverage a single algorithm to try and solve a broad range of problems. So we should try and understand what is that algorithm and how does it work. So it's got four components to it. Firstly, it's going to be about learning the model from experience. Okay, so there's going to be a machine learning kind of an approach. It is not going to be some sort of expert system. It's a show, don't tell, and let me figure it out for myself. Secondly, it's going to learn what is important. It's going to learn the data representation, the comparables, if you will, simultaneously with learning the model. Okay, so even if you feed it pictures, a lot of input, it's going to figure out how it should summarize and abstract that information in order to glean what's most important. Thirdly, it's going to understand the world as a hierarchy of concepts. So it's going to try and break things down into pieces that are relatively easy to analyze, and then kind of glue them back together and to say that a real world construct has got a number of different attributes that are then sort of bundled together to create the high level concept. So for an example, that would be if you are identifying cars, you could think about the color of the car, the size, is it a private passenger vehicle or a truck or what have you, how many doors has it got? It has a number of attributes that each individually is relatively easy to identify. And as you think about color, for example, you actually would specialize into a color identifier. It doesn't matter what you're identifying the color of. That's a module that you can sort of stash away, and then you can bring that to bear for not just cars, but rooms or trees or whatever it is. You can redeploy that same element. And then fourthly, there's a recognition that the hierarchy of concepts is quite complicated. It's got many, many layers, which leads us to what's become known as deep learning, the idea that there's a lot of different attributes needed to characterize a given concept. So we can apply this kind of approach to image recognition. So we sort of got the classic picture of a neural network showing the graphic on the right there. So there's a fairly blurry image, but I think everyone would be able to recognize that as a person wearing a t-shirt, possibly with sunglasses and a visor on, and a backpack. So how does the computer go about looking at this? Well, we start with the sort of visible pixels that we've got, so the raw data, if you will. And you can just sort of chunk that out. You can see there's an area of blue, which is the t-shirt. There's a sort of areas of sort of pale pinky brown color, which is the skin, and then there's a sort of background behind that. So that's easy. That just kind of comes in as raw data. But then we can start to do transformations on that. So for example, if we imagine that the pixel values there laid out in a grid, if we took the differences between rows or columns, we would detect horizontal and vertical lines, right? So if you imagine taking a difference between two consecutive columns, if you're in the t-shirt, the difference is 0, but where the t-shirt strips over to the shoulder strap, you'd get a difference there, and that would pick out that edge. Okay, so by manipulating the data, you can create new features from the original input information, and that would maybe be our first hidden layer there. And this would have done some differencing, and it would have created edges. And then we can do higher level differences, and we can figure out things like corners and contours of coloring. And you can keep going. It'll detect texture and things for you. And you can then put all of this together, and if you've got enough training data, pop out with whether I think this is a car, animal, person, or whatever. So it's starting off with very unprocessed data. It's applying a series of processes to that to create new data elements, which it is, you're not telling it how to do that. It's doing that for itself. And then it's combining both the original data and the new data to come up with its final conclusion. So this is a very long history. We've been doing this, back into the 50s, I think, AI has been around. There's been some evolution. We've talked about moving from sort of knowledge-based and expert systems to machine learning approaches. We've talked about the importance of the representation of the data, how we figure out what comparables are, and there's algorithms that do just that. And then neural networks, which is sort of what we were describing there, as they got deeper and had more levels, became called kind of deep learning. But this hasn't always performed as expected. And in fact, it's really over in sort of the last 10 years or so where it's really, really taken off. You can ask, well, why is that? Why is AI working now? And it comes down to three things. There's better algorithms, we have more data, and we have the ability to build bigger models. And the three gentlemen shown on the right here, Benjo, Hinton, and LeCun, who they won the Turing Award in 2019, which is kind of like the Nobel Prize of computing for their contributions to this. And a lot of what we'll discuss is work that goes back to these three. So if we begin with better algorithms, we talked about this idea of representing objects as a hierarchy of concepts, and that you need a lot of levels of that for it to be difficult. Before 2006, these deep networks, as they're called, were believed to be very difficult to train. And then there was this algorithm by Jeff Hinton that was published in 2006 that allowed deeper, more complex models to be trained in a reasonable period of time. And that can be really regarded as the sort of beginning of the deep learning era. And you can see this is the Google Scholar citation for this. You can see this was actually, I put this presentation together last year. At this point, it had 12,400 citations. Just for reference, today it's got, I checked this morning, it's got 14,600 citations. So it's basically picked up 2,000 citations in a year. And I think the academics on the line will know that that's pretty amazing to have that many citations. It tells you, it gives you some indication of the sheer number of people who are working in this area. This isn't people who've read the paper. This is people who've read the paper, done some research on their own, and they've written their own paper kind of developing their idea. So one of the reasons that we're making so much progress in AI is the fact that there are simply so many people working. And just for context here, one of my personal favorite papers on actuarial science, 77 citations for a paper that I wrote in 1999, and it's all the way up to 80 now a year later. So we're making slow progress there. So actuarial science, much smaller space than artificial intelligence. The second reason that AI is working better now is that we have more data. So this is Internet of Things, big data, digitization of society. We're all familiar with this. And essentially, the more data you've got, kind of the less skill you need to train the model, because the data will just speak for itself, and you'll have sort of all the special cases that you're trying to figure out. And I'm often asked, well, how much data do you need? So there's some rules of thumb on that if you're trying to do sort of supervised deep learning classification algorithm, you can generally expect to achieve sort of acceptable performance with about 5,000 label examples per category that you're trying to classify into. And you can keep going. And if you get to sort of 10 million examples, you can probably match or even exceed human performance with that type of classification. So somewhere between 5,000 for acceptable, 10 million for stellar. We'll come back to those numbers later on in insurance context. And then finally, the third reason is bigger models. Bigger models enabled by the better algorithms and the technology. We have bigger computers. And the size of the model, there's two components here. One is we think about the sort of neuron analogy. One would be just simply the number of neurons, and the other would be the connectivity of the neurons. And it turns out that connectivity is not actually the major feature for biological brains. That neurons are not massively densely connected, but there's just an enormous number of them. The little graphic on the right there shows you a human brain has about 10 to the 11 neurons, so about 100 billion neurons. Models that we have at the moment are in the sort of million range. So we're about 5 orders of magnitude too small. And it shouldn't be a stunning surprise that when you're dealing with a sort of mechanical brain, if you will, that's about as complex as a bee brain or an ant brain, it maybe can't achieve that much, other than in certain sort of very specific areas. However, the current progress is that, you know, we've got a sort of Moore's law thing going on here. A number of neurons in the models are doubling about every 2.4 years. So we should get up to human brain levels of complexity by 2050. I would recommend very highly, if you're interested in this area, there's a book called Deep Learning. You notice Benjio, one of the authors here. This is freely available online. If you look, you can get the PDF. And it's a fantastic introduction. The first chapter is written at a pretty high level, and then it gets more complex as you go along. I noticed in the year since I wrote this deck, this basically almost doubled its number of citations. It's picking up about 27 citations a day. So this is very much the go-to reference. It's also interesting. The picture on the front is a dreamscape picture of Central Park in New York City. It's actually very close to where I live. I thought when I looked at it the first few times, but if you look at it very closely, you can see the middle building on the sort of left is actually a little animal. This is an entirely computer-generated image. This isn't a photograph at all, but it was trained off images from around the center. It was a kind of interesting cover. All right, so let's think about when does this technology work well, and try and think about why it works and how that might apply to insurance. So it works well, it works stunningly well in static rules-based environments where you've got some sort of stationary process. You've got a clean, direct way of observing the data that you want to see. You've got essentially limitless data, and there's a definitive right answer. Okay, so playing games like chess and Go is the perfect example of this, right? You know the rules, it's not going to change, you know who won, and you can just have the computer play against itself to generate as much data as you want. So those situations getting fantastic results, right? And the AlphaGo triumph over the Go Grandmaster a few years ago came well ahead of when people had thought. In more real life, the very good work for driverless cars around things like pedestrian detection. Computers are actually better at traffic sign classification than people. Although you could wonder whether that's a moral hazard problem that, no officer, I didn't see that sign, but nonetheless, computers are at or exceeding human levels of competence there. How does this compare with insurance data? Well, insurance data is kind of characterized by the Merton's principle of reflexivity, which is that we've got a number of behavioral feedbacks and a dynamic system that reacts as we learn more about how it works. So it's not a fixed stationary process, it's an evolving process. We also deal often with proxy data, not direct data. I never actually get to observe your true annual expected claim frequency on your auto policy. You either have a claim, in which case I see one claim, or you didn't, in which case I see none, but your actual frequency is some number around 5 or 10%, and I never actually see that. And then for losses, we know, if you're in the liability area, and that was what Ron's excellent presentation about reserving was, you don't even know what the ultimate losses are in a lot of lines for many, many years until it's sort of way out of date. So we don't get a clean, direct observation. We get a dirty, indirect observation of most of our data. Nonetheless, we find AI works really, really well on certain types of real-world data, which leads us to suspect that there must be a reason associated with the data as to why it works well, okay? And so what are some characteristics that we see in real-world data? Well, it's often presented to us that it looks like real-world data is extremely high dimensional, which means that there's millions and millions of different possibilities for the data. But that in fact, there's some hidden structure lying there, which if you could tease out would give you a great deal of insight. And it's that ability to tease out that hidden structure that is what makes AI work. And photographs are a good example. The collection of photographs, so if you imagine a photograph that's 1,000 pixels by 1,000 pixels, say, for example, even if it's just black and white, it's a million data points went in there, right? There's just an unimaginably enormous number of potential images that you could make. But a photograph is not a random image. So what I've got here is, what have we got? 20 different simulated images, okay? And if you show these to a computer, the computer would say, hey, these are all completely different, because if you imagine where they are as a point in a 1,000-dimensional space, they'd be very evenly distributed around that space. Okay, so they would, to a computer, all appear completely different. To us, they all appear exactly the same. I don't know, you could even distinguish. You have to look very, very closely to distinguish these, and none of them look like actual pictures. So what's going on here is, if we think about actual pictures of actual, scenery and faces and people and buildings and cars and objects, those images live in a very low dimensional subspace of the space of all photographs. So there's some hidden structure there that all photographs have in common that gives us some hope that if we could determine that, we would get a great deal of insight out of it, and we would be able to make predictions. And the sort of characteristics that you've got here is, your photograph it's continuous. It doesn't have you don't have a picture where if you morph it a little bit, it suddenly ceases to be a picture. It's sort of a little open subset, but it's a very small part of the set of possible photographs. So there are a number of helpful rules of thumb around this about what makes real data so special. Another paper by Bengio, where he characterizes, in particular, the data is a low-dimensional subset of what appears to be the space of possible samples. It's sparse within that. It often has sort of hierarchical organizations. And then it'll also often have a temporal and causal coherence to it, which you can leverage in modeling. What applications can we have to this for insurance? There's a number of sort of general business fit things, which I won't discuss because they're not especially insurance specific, although I would pull out fraud detection as an area where, from a pattern matching perspective, there's been a lot of success. There's potential in a number of areas around underwriting, sort of higher frequency lines where you get a lot of data and people could fall into broad classifications, possibly underwriting accounts based on broad publicly available information. And let's just go back to that question of how much data do you need, and think about the sort of size of the line of business. It's an important thing to triangulate. So remember, we said to get good performance from a classifier, you want about 5,000 observations. So you want to see 5,000 claims, basically. We want to classify people into maybe high claim likelihood, low claim likelihood. So we need to see a decent number of claims. So the number of exposures you need depends on the claim frequency rate. At a 10% frequency, you'd need 50,000 exposures. If you're trying to pick up something that's a 1 in 1,000 per year per insured, you need 5 million exposures. So that's quite doable from an auto perspective, right? There's 150 million drivers or so in the US. So decent sized company is easily going to get 5 million exposures, and you could expect that sort of resolution. But if you're in a more specialty line, you're doing roofing contractors or something, and some particular part of GL, you very quickly get into situations where your risks are significantly different that you won't ever get 5 million exposures. So there can be definite data granularity restrictions on applying some of these techniques. I want to end with a couple of comments about bias in modeling. This is obviously something that's, I think, quite front of mind at the moment. And there's worry that these algorithms can have hidden bias to them and really pick up things that maybe you are not, you're prohibited from rating. Certainly the actuaries and the regulators are very concerned about this. It's important here to recognize that this is not a new phenomenon. Statisticians have known for a long time that if you're going to train you're going to train a model on data, it must be a random cross-section of the population. You go back to the famous Dewey defeats Truman election call after the war, where there was a poll done, but it was only done of people who had telephones, which at the time was overwhelmingly Republicans, and they called it election because they didn't have a random. The statisticians have been aware of this, are aware of this. The problem that we have is as we apply these AI techniques, the machines kind of quote unquote see things in images which we don't see, and they look at them in a different way. So you can have a biased sample of data that you're feeding into your model, but not be aware that it's biased. But really, this is not a matter of building some brand new technology that no one's thought about. It's really, to solve this problem is a matter of enhancing existing skills that statisticians have around managing training data and doing testing of it to ensure that it truly is a random cross-section. And I'd also note that models can fail. We often talk about sort of quote unquote biased algorithm. It's almost never, normally algorithms are just math. They're not biased one way or another. Least squares or maximum likelihood isn't biased. It might be a biased implementation, or it might be a good implementation run by a biased bureaucracy. So there's sort of different levels at which these models can fail. And I think we need to always keep in mind that as we worry about machine learning, we at least have the potential to understand how an AI model is making a decision, which we probably never would truly understand how a person would make a decision. So I think this is it's a very real problem. I don't want to downplay it, but I think it's a problem that we will be able to address. We just need to focus on it going forward to make sure that our training data is. So to summarize, I think three things that I'd like you to remember out of this talk. Firstly is that artificial intelligence, when you hear that buzzword, it's a problem domain. It's about solving problems that people find easy, but computers find hard. We've made spectacular progress in AI over the last 10 plus years through bigger models, better algorithms, and more data. And these models work on a show don't tell. The computer figures out what's important. It figures out the representation at the same time as it figures out the model form. And a lot of these models, for their success, do rely on special characteristics of the underlying data. And so if they're applied to data that doesn't have those characteristics, they could potentially fail and disappoint. And that's what you should be looking out for as you consider these applications. So that, I'll hand it back to Michael if there are any questions.